In this video, I'm going to explain to you the logic behind what's called a hypothesis test. Now, suppose you want to know the number of hospital beds in New York City. And let's say, your friend is guessing, and they're saying, I think there are 3,000 empty hospital beds in New York City. And so let's say that, you're not sure, but you think that number is, it might not be right. Well, essentially what you do to test that is a hypothesis test. So you could test and see how confident are we that 3,000 is the number for, remaining empty hospital beds in New York City. So essentially, your hypothesis test, here's how it usually starts. So the logic of it is this, is that we're going to have what's called a null hypothesis. So the null hypothesis, and the null hypothesis is basically the guess. Your buddy's guess is the best way to think about what the null hypothesis is. That's usually called H0. So H sub 0 is the null hypothesis. And in this case, the null hypothesis is that the true mean is 3,000. And let's say that you were, your alternative hypothesis, that's usually either, if you have no prior, belief, then you would just say that, it's not 3,000. But if you think that, I think it's less than 3,000, then your alternative might be, that it's less than 3,000. Or, of course, it might be that it's greater than 3,000. And so these are called a one-sided test because you just want to test if it's one-sided, left or right, versus not equal. Then you're sort of testing, is it greater than or is it less than? These are called a one-sided test versus this is a two-sided test. So whether it's one or two-sided is strictly just based on what your alternative hypothesis is. For the most part, in the social science research, we usually always just do a two-sided test just because we're not really making any judgments. We we don't really, there's no reason for us to think a priori for most things that it's less than or greater than. And so that's why, we just say, all right, yeah, it's just going to be a usual two-sided test. So that's sort of what I'm going to focus on here. So, all right, so again, the logic of this test so far, your buddy made a guess and you want to see whether they're wrong or not. So the way you're going to try to see if they're wrong is you're going to say, all right, well, I'm going to essentially collect a sample. And, let's say you knew the number of hospitals or something. And so you're going into each hospital and you're using that hospital to see how many empty beds they have as like a sample. And then based on that, you'd have a guess for how many empty total beds there are across all of New York City. And so basically you collected a sample, and based on that sample of hospitals, you're projecting that the number of empty beds is going to be your X bar in your sample. According to your sample, the number of empty beds should be, let's say, 2,600. Okay? So, all right, what does that mean? Now, it might be tempting to say, well, there you go. They're wrong because we got a number that's not their guess. But what if your sample average was, 2999 or 3002, I mean, if you get a number really, really close to this, then you kind of can't really say that they're wrong because you only looked at a sample. If you maybe really surveyed every single hospital and you get the true number of empty beds, that you might actually get exactly 3,000, who knows, right? So here's the logic of this. It's that if your sample value is far enough from their guess, from the null hypothesis, then you reject the null hypothesis. So again, that's what's going on. You make a guess, you collect a sample value, and you compare the two, and if it's far enough, you reject. So then the million-dollar question, how do you know if what you got is far enough from this? And that's where we use test statistics. Essentially, we're saying, well, how many, standard errors away from this mean is this sample? And if it's far enough away, then it's pretty much, we don't really believe then that this is the true mean, right? So it's sort of like if so what we're sort of saying, the logic of it's that, all right, you know what, let's go with it. Let's go with our friend's logic, and let's just say, you know what, suppose you're right. Suppose the true thing is 3,000. Well, then the question is, what's the likelihood of me randomly collecting a sample and getting something that's 400 beds shyer than your guess, right? So what's the probability? Again, it's possible. It's possible that the true value is 3,000. The hospitals that I chose maybe were the ones with the least beds, and if I really got at all the hospitals, more beds would be left, and the average would be 3,000. But so it might just happen that I got I got a crazy sample. But the question is, how likely is it? How likely is it for me to have to get a value that's that far below the guess? And that number, that probability of finding a sample as far or further from your guess, is called the p-value. So the p-value is, the definition is literally just the probability of finding a sample as or more extreme as ours. So again, our sample value was 2,600, and so the question is, what's the likelihood? And so really, so that's basically 400 away. Now, because we're doing a two-sided test, we're basically saying, all right, well, yeah, sure, our sample value was 400 less than, the mean, and so to be 400 less or even 400 above the mean, what's the probability of that? What's the probability of us finding in general something that's 400 beds away from the mean? And so that, again, that's the p-value. Now, essentially, what we're getting at here is this. If your value is far enough away, now the farther enough away it is, the lower the shaded red region, right? If this was 2,500 or 2,100, then this would be even less shaded region, right? So the further away, so the moral here is that the further away equals lower p-value, So again, p is the probability of finding what we did for it to be consistent with the null. So again, if what we're finding is really inconsistent with the null, then we're going to get a low p-value, and then we're less likely to believe that this is the truth. So the decision in the end basically boils down to this. If your p-value is less than a certain threshold that you predetermined, usually it's 5%, but in general it's called alpha. So alpha is it's called the significance level. And really what it's saying is it's the threshold. You have to determine this before you even collect data at all. Usually, again, it's 5%. So in most social science research, basically you're checking for if your p-value is less than 5%. And there's nothing that, we don't really solve for alpha. That's just something that we just pick. And so basically, if our p-value is below that threshold, if our p-value is below this, then you reject the null hypothesis. You reject the null. So that's basically how this test works. You have a guess, you collect some data, you see if that guess is far enough, you look specifically at the probability of getting something that far, and if that's really a low probability, then you say, yeah, I'm going to reject the guess. As far as how you exactly find that probability, like I said, that's based on you do a test statistic. So usually this is often sometimes called a t-test. So if somebody were to say do a t-test, they're really just saying, see if these two numbers are far enough from each other or not. And so if they're far enough from each other, your t-test is significant, and you reject the null that they're the same, right? So here, notice the hypothesis was just that it equals a specific value, but more generally, your hypothesis test could be that, hey, do men and women have the same average income, for example? And that's so your null hypothesis in that case is that mu1 equals mu2. And then your alternative could just be that they're not equal, and then you do a t-test, you find a t-value, but again, you don't actually do it in the real world unless you're doing it out by hand, which, in the real world of social science research, you're not. You just have Stata do it. So yeah, you're basically just, you have this, Stata will generate, based on this data, a t-test, and it'll automatically, based on that t, it'll give you the p-value, and then all your job is to look at that p-value, see if it's small enough. If it's below this threshold that you've set, you're going to say, yeah. If it's below, then you say, I'm going to reject this null that these two are the same. So again, if p-value is less than alpha, then you reject. If it's greater than alpha, well, then you basically can't reject, right? We never really accept hypotheses, but you either reject it or you say, hey, I can't rule this thing out. You can never say, oh, yes, therefore it's exactly 3,000 beds, because what if it's 3,001 beds, right? So you can either just reject a number as being too far off from what our data is saying, or that it's consistent with our data. So, and again, the way you find the t, so again, when you collect data, you're going to have your x bar, you're going to have your s, you're going to have your n, your sample size. And so to actually find your test statistic t is just going to be whatever your sample value was minus the null divided by s over root n, because that is the standard error, right? So again, this is just saying that's the number of standard errors away. And once you have your t, again, you could just use that to find your p. Again, this is not something that you actually do on a day-to-day basis at all, or really at all. Even statisticians don't really. We use computers to do that. So essentially, but that's just what it is. So long story short, that's the logic of a hypothesis test.